Many thanks for the kind invitation to this interesting workshop. I'm going to talk essentially a little bit also on my personal history with ultrafast magnetism, and then on ultrafast logic functionality, not just about switching, but maybe on some other functions. This work has been done in the last years by George Lefkidis, a senior lecturer in my group, 2 PhD students, and 2 people who used to be in my group and became professors in China. So here I have to say something about the history, my personal history also with that field, and then I will go to results on logic functions after I introduce the theory. Then I will go to 3 magnetic centers and to 4 magnetic centers. So about the history, it's very clear to start with this view graph, and actually, we owe a lot to Eric Beaurepaire and Jean-Yves Bigot, who sadly passed away this year. Actually, I have to say that I knew these data already in 1995, when Eric Beaurepaire came to Berlin to a group meeting of the Baberschke group, and this was announced as a very record-breaking speed limit of magnetization, sort of in the abstract, so I got caught by this title, and even more by the contents of this relatively little group meeting, 10, 15 people being there. And then we got into contact, we discussed and I got the opportunity to go to Strasbourg, and I went there for 6 months in 1996 and early 1997. So I am maybe even more indebted to Eric Beaurepaire and Jean-Yves Bigot for their hospitality and for this very rich time at this 20 years or 22 years ago. So here we see an ultrafast demagnetization that has been shown very many times. But the question is also, what is the lasting effect of this paper? Not just what is the momentaneous thing. And the lasting effect, I think, one of the 2 things that I would like to mention has already been mentioned by Peter Oppenauer. It sped up the time limit of magnetization dynamics by 3 orders of magnitude. Before 1996, people were also striving to find the ultra-fast or the fastest possible magnetization dynamics, and this is evidenced by the paper by Vaterlaus, Beutler and Meyer, the Zurich group, and they found something like 100 picoseconds is the speed limit, and this was considered to very fast due to phonon-magnon coupling. And this, of course, makes things faster by, say, 3 orders of magnitude, as Peter Oppenauer has emphasized. There's a second thing which made us know something that is qualitatively different compared to the Vaterlaus et al. Paper, that is the order, the sequence of these curves. If you do a picosecond or sub-nanosecond experiment, then people thought, in typical magnetic recording, you heat up the lattice, and then due to a phonon-magnon coupling, the spins will follow the lattice temperature essentially. And after 1996, we learned that the order of the blue and black curves is reversed. This used to be a qualitative novelty that came about in 1996, and irrespective of debates about details of mechanisms and various aspects of various materials, I think that's a lasting novelty, just reversing 2 curves in 3 paths. Now, going on, there's a lot of whole zoo of interactions, of course. I show you a few of my old slides here also to show you how tedious it was to go in that field in the beginning. Most of you are maybe entered a little bit afterwards. So there's, of course, the instantaneous pulse duration, electron-photon coupling. Then magnetism, I have to stress it again to the non-theorists, of course, is not predominantly spin-spin coupling. It is predominantly electron-electron interaction plus Pauli principle. So the correlation of electrons is very important for magnetism. Then, of course, the phonons kick in. And we have phonon-phonon and harmonicities and phonon-magnon coupling as another time scale. The first attempt of my group then, already in Halle, with Guoping Zhang, who is a professor in Indiana State University now, was the following. we could not handle laser pulses, so we started with a predefined excited state population. And we looked for the time-dependent optical and magneto-optical susceptibilities as a function of this excitation width, the spectral width of this excitation. And then you can see two different things. The first one is there is a width dependence. So if the width is something like 20 electron volts, then we see a narrow dephasing distribution since the speed is fast, since many channels contribute. If the width is narrow, then the speed is delayed here. Yeah, that's one thing. And of course, this is a non-magnetic effect. It is present in the magnetic and the non-magnetic channels. But this gives rise to something that has been elaborated on by Bert Koopmans in 2000 then with this optical artifact, bleaching. Is there a magnetic effect at all? So there was a heavy debate questioning whether there might be a magnetic effect at all in this femtomagnetism, as it was termed in the BIGO experiment. Here already we can see there is a difference in the magneto-optic time-dependent susceptibility compared to the diagonal one, the optical one. So if we elaborate more on that, we see there is a different dephasing dynamics of this excited state distribution, say 18 femtoseconds for the charges and 28 femtoseconds for the spins. The spins lag behind the electrons, which I will explain on the next slide. But I should stress also that historically speaking, these times, which are now common in experiments of the Ashleyman group, of many other groups, these times were not to the taste of the experimentalists, yeah, at that time. It is very clear that they said it's absolutely wrong what I am doing, and we need to see something that is 300 femtoseconds here. Yeah, it cannot be, and so on. Yeah, so this is very clear that things have evolved over those 2 decades. Why is charge and spin dephasing different? So nickel has 2 holes in the D shell. For simplicity, the theory goes as follows. We have a highly correlated nickel atom with a Hubbard-Ewan exchange and an exchange anisotropy. We plug the single center in a repeated lattice and couple to the bands of nickel. And then we find that the excited states dephase differently depending on whether we have triplets or singlets. 2 holes in the D shell give rise to a correlated set of states of triplets and singlets, and only the triplets contribute magnetically. This is a subset. So spins use only a subset of dephasing channels, thus they are slightly slower, while charges use all states. That's a short result. Of course, we were squeezed to do the laser, yeah? And then what shall we do with the laser? The laser doesn't couple to the spins, so we have to introduce spin-orbit coupling to do that. And so in the combination of introducing a laser field and spin-orbit coupling to this highly correlated band structure plus single side nickel situation, we found that the predominant ground state property is a triplet, magnetic property, and laser excitation brings us more to the singlet regime, which amounts to some demagnetization and something also too short scale at that time for experimentalists of something like 40 femtoseconds, but showing there is a true magnetic effect in this situation. However, you could not switch. We were very disappointed. And so the reason why we could not switch was that the excitation did not last long enough in this broad band, still relatively broad band structure of nickel. So we could not localize this excitation. Switching always means somehow the interplay of speed and localization. And so we thought maybe we go to nickel oxide, which was very popular at that time, where we have narrower bands and intra-gap D transitions. And then we took just 1 sublattice, since 2 were too expensive. We could not handle 2 nickel with quantum chemistry at that time. And then we could switch this sublattice. The other one would switch oppositely then, of course, of nickel oxide with the laser pulse repeatedly without too much loss of the signal. So the narrow band material could be switched. The wide band material could not be switched. And the question is angular momentum conserved? Yeah, angular momentum is conserved in the universe. Fine, that's what we believe. And we came up with this laser-induced process by saying at the vertex angular momentum is conserved. The photon, the external world, has to bring some angular momentum or to get it or so, yeah. And so we absorb with circular polarization and then we emit with circular polarization and ultimately we switch in this combination. And since quantum mechanics is time reversible, one cannot distinguish absorption and emission, strictly speaking, in quantum mechanics. So a phase relationship substitutes for that. So the incoming polarization has a different velocity. That's what we see here, right? Than the outgoing polarization. And in this way, we see due to this phase relationship that angular momentum is conserved during this switching process. And we use this fourth component, I guess, of this Stokes vector to indicate that. Then the question is phonons. Phonons were a hype. They are still a hype. Yeah, we forgot about them. Yeah, since we didn't see a matrix element to couple to them, but we were forced by experimentalists to induce phonons. Okay, then we did it, and we found, first of all, if we neglect phonons, then we have this elbow structure. I think it's very similar to what Jeff Boker indicated yesterday to us, where we play with increased fluence versus increased speed, increased duration of the pulse, and red means switching, blue means unswitched, and white means neutral or towards switching, so to speak. Yeah? And if we add phonons, then the only effect that we got from phonons is that we get a replica of this elbow structure, since it means that the vibration of phonons just brings us back occasionally with the phonon mode to the favorable switching conditions. This is what we see. We see that switching occurs not only in a certain condition, but every time that the phonon brings us back to the favorable conditions. And finally, yeah, this is a question of the probe pulse. I skipped that. We did also a probe pulse, included that. That's not so important here. Yeah? Finally, the earliest work that I did was to think about the old-fashioned spin lattice relaxation, essentially following the approach from Jeffries and Scott and Jeffries in 1962 in Titel's group in Berkeley about the various electron spin resonance mechanisms, and I employed this Raman mechanism. This is this one with phonon in, out, yeah, accompanied by spin flip, and doing that and transferring that to the then modern world of magnetic anisotropies in, say, gadolinium. I found a time scale of something like 48 picoseconds. But of course, using such a formula in the context of bands and electronic states and anisotropies is very risky from today's perspective, of course. And I should also stress, in all these mechanisms, the temperature dependence is extremely steep. So there is a narrow window where one can really play with the temperature only, and the temperature dependence is to the power of, I don't know, 6 or 7 or so. Yeah, I should give this warning. Okay, what we found in these old times was there is an optical artifact, there is dephasing, there is population dynamics, everything very fast. Nowadays accepted, speed is accepted, but at those times it was too fast for the experiments at that time. Then we have the phonons with this replica structure and this very old 48 picosecond result on gadolinium. Now, of course, we cannot be satisfied with these old results. Let's go to more modern things about, we switched to quantum chemistry to address molecules, to see what can a bottom-up approach do for us, molecules, which means we have quantum chemistry, just we can address a few centers in real space and so on. Yeah? Since ferromagnets could not be switched due to the broad bands in our picture, antiferromagnets are good, but we have this crystal structure, which is too complicated for us. Still, we have two magnetic centers, which is good. And I personally learned from Theo Rasing this exchange enhancement effect in the antiferromagnets, also then of course motivating a lot of experimental work in that direction. Let's go one step further to magnetic molecules, where we have discrete levels, good addressability, active centers, but of course only very small systems. And the difficulty is even harder. These molecular people don't act in the field of ultrafast magnetism. They come from very different communities, and so these molecules come from very different environment. So we have slick and stabilized situations, one nickel here, one nickel there, many, in our view, of course, superfluous ligands, more or less. Yeah. Then we have gas phase clusters with nozzle expansion production. Or we have what we would like to see for devices, some arrays on surfaces. But here I also have to give a warning. Of course, this is what we like, yeah? But the structure is not that well known in detail to the taste of the theorists as one might expect compared to the structural knowledge about these synthesized structures. Yeah? So if you look to the very details, there is still a size distribution. There is still a local geometry distribution, even in the structure. And what is worse, the more also in magnetism. Yeah? I have to say that. So it is not as precise for us as theorists as in the molecules. And of course, we can think of protecting magnetic molecules by cages and so on. Yeah? Now, I showed this to a referee. Yeah, we have to be worried about competitors, non-magnetic competitors. And the referee says, oh, it will never go like that. The magnetism will always win. I didn't get the money showing this slide at that time. Yeah, we see competition is strong. Yeah, more or less, we should think of something, not just of memories, if we think of novel directions in magnetism. So in molecules, we need a mechanism for switching. We go for the lambda process, which means we bypass this direct Zeeman split situation, which is forbidden in the electric dipole approximation. It would be a slow magnetic dipole transition by two electric dipole transitions. And this is the process. And of course, one could say if temperature already wipes out this difference, yeah, we are not in good shape here, yeah. Nevertheless, I would like to stress that a small imbalance that we can get if we have a Zeeman field in an ensemble of molecules can be enhanced by the selection rules due to spin-orbit coupling in excited states. So situation may not be that bad in molecules, although of course you would like to see this as an array on surfaces. Nevertheless, also molecules start to develop an anisotropy. The anisotropy per molecule is much larger than the anisotropy per atom in a solid environment, of course, or even on the surface. But of course, we don't have that many centers. That's also clear. Now, let's go there. How many centers do we need? What can we expect? If we have one center that's like arc or surfaces, we can switch locally. If we have two centers, we can also transfer spin from one to the other. If we have three centers, we can circle around, and we can produce, in the presence of an active field, even a logic OR gate. With four centers, the field can be static, inactive, just being there, and we also can produce a gate. Yeah? So this is what to expect. So 4 centers is already good for these things. The Hamiltonian is a very highly correlated Hamiltonian for quantum chemistry, together with spin-orbit coupling, with B-field coupling to the orbital momentum, to the spin, maybe phonons, maybe not. The laser dynamics is included here with propagation. Okay. And we do Hartree-Fock for the ground state. Then we do coupled cluster with singles and doubles for the correlated reference state, but that's just the reference state. We do much more. We do the equation of motion coupled cluster theory with singles and doubles, meaning that on top of the highly correlated reference state, we get the excited state excitations. So that's really meant for dynamic correlations in excited states, as is usually the case in spin dynamics. So roughly speaking, this is multiples of a minute, this is multiples of an hour, and this is maybe multiples of a month. Yeah. Now we have magnetic molecules, strong correlation, spin-orbit coupling, and laser-induced lambda processes as ingredients. We start with this mercaptane molecule, which was synthesized in Kaiserslautern. And this nickel is magnetic, it's a triplet, and this nickel is non-magnetic. So some of the magnetic centers may be non-magnetic in molecules. And if we try to address the excitation of these states, we find the following situation. We can think of a process that switches this nickel locally and is accompanied by a charge transfer to the ligands of that nickel, which is magnetically inert. So this is a thing one could not have found if one had not the combination of experiment and theory in this situation. So you see here the switching of the three, we have three expectation values of the x, y, z components. Just watch the z component from plus to minus or minus to plus here, from here to there, is accompanied by a charge transfer in this indicated in red, roughly speaking. Yeah? Now, three magnetic centers. I invented a molecule as a test case, which has three nickels in different local positions, bridged by sodium. And Berg Koppmann sent us a student, Sandra Kersten, and we found then we can indicate here a local spin flip here or there, and we can have a spin transfer around the corner. And from these building blocks, we managed essentially to produce the truth table of an AND gate, indicated by the input being the position of the spin localization, and the second input, unfortunately, being the direction of the B field, which is bad since the B field sets then the slow scale of the dynamics. We could not do better. Yeah? We also could produce an OR gate, as is indicated here, or an XOR gate, similar to the quantum C0 gate. Still, okay, that's something. Next functionality could be erase. What is erase? Erase means white goes to black and black stays black. So we have to break a time reversal symmetry in a way, and there are various options. One is a chirp pass. We tested a chirp pass. The chirp pass detunes, ramps up the frequency, and in this way it detunes the fidelity from, say, nearly 100% to 80%. And doing it several times may erase in such a situation. That's one option. The second option is to reverse the direction of a process. Of course, if you start from an initial state distribution, go to a final state distribution, and you reverse it, yeah, that's fine. That's quantum mechanics, fully reversible Schrödinger equation picture. That's what one wants to have. But in reality, what one has is one has also not the full fidelity. One has also some occupations over there. And if you reverse it, that's also fine. It's also quantum mechanics. But in practice, one does the following. One starts from one final occupation in one state, and then one gets, of course, something that is very different. And this breaks time reversal in the wanted sense that one can erase. And so if we have a dimer, cobalt iron dimer bridged by oxygen, then we end up in the state C in a sequence of different pulses, no matter which spin or situation we start from. Yeah? And this is accompanied by the Shannon entropy as an entanglement measure, if you like, or an information measure. So the information is gained, the entropy decreases from 2 to 0.31. So that's an erase functionality. Now, the next part is we can cycle around. I just go through that quickly here in a pictorial way. So we can cycle a cobalt trimer in the gas phase, which has also been synthesized by nozzle expansion. We can do more with force centers, as I would like to show you in the last part of the talk. Force centers I can do myself, actually. I like doing these calculations myself. And so there's a lot of group theory involved. I like group theory very much. Group theory is here involved in the symmetry breaking from the square to the rectangle to the trapezoidal deformation to the one-sided deformation, adding spin-orbit coupling, getting many irreducible representations, and so on. So it's very nice theory. I should really recommend that. And then doing that, we can get the vibrational spectra. We can do many things, yeah? And nickel 4 has 4 different sides, and this is slightly distorted. And of course, we can try first with this ab initio theory, local switching on this, on that, on that, and that side as before. This is possible. This is hard work, but it is possible, so I don't want to bore you with that. It is also possible to switch from there to there to there, to switch the spin localization. It's also hard work, but after maybe a couple of months, one achieves all these functionalities. But one can do more. One can also exploit the phase of the states and branch out the spin localization from here to two centers simultaneously. So that's half a step towards quantum information, only half a step. Yeah, it's nothing spectacular, but still it's worth trying it with a wave function method. And then one can use this step to say that the history of the path traveled by the spin from the left center localization to the right center localization, it can be, the path can be traced back due to the phase interference in the final state phase, whether you go through this nickel alone or through both of them. Yeah? So that's a functionality exploiting this phase difference. And we can also do a cycle, we can also do a shift register, and we can also do an OR gate. But we can go another half step towards quantum information, and people tell us, why not using this universal square root of NOT gate? Yeah? I think Professor Chloe in this building is always advocating and squeezing us, we need to do that. Yeah, okay, why not doing that? Yeah. What is a NOT gate is very easy. Yeah? 0 goes to 1 and 1 goes to 0. And the square root of that gate is this operation here. Yeah? The square of this matrix is the NOT gate. So this means two identical pulses should give us the NOT operation. And so we also tried hard. It looks so smooth here, but it's also hard work. And then after 2 pulses, we get the NOT operation. And if you stop in the middle here, and beware, here it's picoseconds, so it's 1 picosecond rise time, maybe roughly speaking or so, yeah. So it's slower, but still it is feasible in these structures, yeah. And carbon is important, and this is more or less the last message I would like to show you. Teresa Kuberis, who was in Kindle's group in Berlin actually a long time ago, showed these results when she was also then postdoc in Zurich later on, that C60 is very robust. One can play soccer with the STM here and do this abacus. This is C60 supported nanologic in a way, yeah? And so this is interesting, yeah? And gives us a motivation to dig deeper into carbon. I did a mistake. I bridged these centers with sodium, thinking sodium simplest S electrons. We have to pay so much price for this quantum chemistry. We wanted to have a cheap bridge, yeah? And I overlooked what is known also in this building. I learned from Eva Rentschler, the Kanamori good enough rules. And if you have S electrons, then all those magnets want to be antiferromagnetically coupled, essentially. This is what chemists know. Sorry, I'm a physicist, I didn't know that, yeah? And, but there are certain very narrow windows where the Kanamori good enough rules give a preferential ferromagnetic coupling. And then I said, okay, if graphene is spin polarized, combining that, yeah, let's do p electrons, and then we can transfer spins. And this is in fact what happens. And in this way, we can reach this. Yeah, many people said how to scale down to the CMOS scale of 5 to 10 nanometers. We have to say how to scale up to the CMOS scale from a single 3 angstrom molecule to something like 10 nanometers. Yeah, and so in fact, what we can do with this method is we can really have a magnetic entity here and a magnetic entity very far away, and applying this p orbital degeneracies, and in fact, ab initio quantum chemistry can handle a 10 nanometer situation of spin transport, transfer, fully ab initio quantum chemical with a wave function. Yeah, that's possible. So I would like really to publish that, and it's unpublished, and to go further also in that direction. Now, this means we can transfer spin polarization due to the dynamic version of Gardiner-Kanamori rules in zigzag p chains, I would say. Yeah, good. Summarizing, I showed you a few of those and/or erase, shift, and other functionalities in 2 and 3 magnetic centers. I showed you that we can have pure spin logic without the active magnetic field in 4 magnetic centers, playing with hard-working, tough quantum chemistry, quantum interference effects, square root of naught logic, and I advocate something I learned it the hard way, that p orbitals might help us to bring quantum chemistry, maybe also the experimental version of that, to some long-range spin transfer, since the damping is not as strong as it is in the S channel. Many thanks for your attention.